A very warm welcome. My name is Tanmay and I'm a final year student studying in Anna Sahib Dange College of Engineering and Technology, ASTA, in the Aeronautical Engineering Department. I'm here to present my topic Emerging Technologies, MEMS and MEMS Hybrid Propulsion Systems for the ISA2 video presentation. So this is the list of contents which we'll be going through. First, we'll have a look at the introduction. Then we'll see the materials for MEMS required for manufacturing it. After that, we'll move on to classification. It includes the chemical propulsion and the electric propulsion and some other propulsion systems, which you can see over here. So under chemical propulsion, we'll see solid microthrusters, micromonopropellant thrusters, cold gas thrusters. Under electric, we have one that is colloidal colloid thrusters, and in other propulsion systems we have vaporizing liquid, plasma, colloidal electrospray, free molecular micro resistor jets, and cold gas microstructures. And finally we will see the aerospace applications along with some commercial applications of MEMS systems. The word MEMS stands for Micro Electromechanical Systems. It was introduced in the year 1986. It is also known as either microelectronic or micro electromechanical systems. So this area is relatively a new area and it involves a drastic reduction of thruster size and mass. So this is mainly due to two reasons. The first one is when there was like computer and microstructure manufacturing. So it had many much disruptive and drastic advancements, and many spacecraft components such as science payloads, which includes cameras, sensors, etc., or even onboard computers. So thus their size kept on reducing and reducing. When you see our old computers and our modern computers, they're very much less weight and much more faster. So this enabled a new generation of microsatellites, and it can be launched at much lower costs. This can be launched one time, and the risk of failure is also distributed and less. So these come under like future Mars missions are present, and it is under evaluation. So all these new space programs need propulsion systems which have reduced size and mass. And the second reason is that micro propulsion technology can reduce the thrust to mass ratio, and in some cases the power to thrust ratio itself. So therefore, there are many parallels which can achieve the same thrust from normal propulsion devices, but at a reduced mass and power requirement. So this improves the mass ratio in the rocket equation of Sokolow's equation and increases the capability of the spacecraft. So normally the weight is below 100 kgs, and the new design it's below 10 kgs, and even 1 kg, that is picosat, and 10 kg, which is also known as nanosat. So such satellites require highly integrated propulsion system technologies which are manufactured using MEMS systems. So the component size can be from 0.001 to zero point 0.1 mm, and there is one central unit which processes the data, and it has an IC chip. It's known as microprocessor, and other components which are microsensors. It has a large surface to volume ratio, and the forces produced due to electromagnetism, that is electricity and magnetism, and fluid dynamics properties like viscosity. These are important, or much more important, while designing it. And it comes from the molecular nanotechnology itself. Here is an image of the first draft which proposed the MEMS systems. To have thrust, we need to manufacture the system itself. So MEMS involves production using a semiconductor device, and for that fabrication, many layers are deposited one above the other, and such a pattern is formed by photolithography and etching to produce the required shapes. Here is an image of an uh, TIN beam, and this is the zoomed image for the same. So the common materials are silicon, as it's used to create IC circuits. It is more reliable and causes very less fatigue, and it works for billions or sometimes even trillions of cycles. Next is polymer, as silicon is much more expensive. It is very economic to use polymer for many companies, and its major applications is in microfluid properties. Next is metals. They have a high degree of reliability, and these are some commonly used metals like gold, titanium, aluminum, silver. And the last one is ceramic, which is highly resistant against biocorrosion in the propulsion systems, and it has a very high electrical conductivity with a large elastic modulus. Coming on to the first type is chemical propulsion. Here we have a solid microthrusters first. Here we can see an image of the solid microthruster. It is very much small in size, and it consists of multitude of fabricated single shot thrusters. And here we can see it is a silicon wafer, and above that everything is placed. It is a 3.3 into 3.3 silicon square, and each one of the element has its own individual ignition ability. So there's a megapixel microthruster, and it follows a two-stage approach where the first stage, it is thermally denotable, and stiffenate is heated, and it actually auto ignites at 270 degrees Celsius. After that, which it explodes and releases lot of energy with a non-stable, non-usable momentum. So in the second stage, after once it's exploded, and it ignites a special mixture, which is a nitrocellular mixture from zero point 0.5 to 8 microgram, which creates thrust, but there is no byproduct of the system. As we have, when we have chemical reaction, we have several byproducts, but we don't have byproducts here. So the total mass is around a few grams, and the specific impulse in between 100 to 300 seconds, and 10 megawatt of power is required for its ignition. The type which we have under chemical propulsion is micropropellant monothruster. So it is currently being developed by NASA's Goddard Space Flight Center, and it is mostly to be used in nanosatellites, and its performance goals are around thrust of 10 to 500 micronewton, along with a specific impulse of 240 seconds, and it's ranged from 1 to 1000 micronewton second. So one major investigation is the fuel choice, and for that the freezing point is low. So no heaters are required, and the design is hence simplified. So they work with Primex, and they suggest that a mixture of hydrazine, that is N2H4 with HN, and water with a freezing point of minus 2 degrees Celsius is required. And the next one is cold gas thruster. So it is a very simple form of rocket technology, and they use a pressurized gas, which is very commonly available, that is nitrogen, and it is fed through a valve and a nozzle. So it is currently under the Armstrong Space Technology Center in Sweden, and it is under research. And along with that, it has four cold gas thrusters, and which are integrated into one system. And with the help of a piezoelectric valve, it's assembled into a silicon wafer, as we previously saw. And you can see over here, this is a micro nozzle of an MEMS system. So its target is around 100 micronewtons of thrust, and each thruster weighs around 70 grams. Coming on to the next type, we have electric propulsion, and under this we have the colloidal thruster. So a colloidal thruster uses capillary tubes for the propellant feeding system. So there are very highly miniaturized needles, which we can see over here. This is the microcapillary structure, and you can see the small needles which point out. So even a miniature volcano can be formed with the help of silicon when it's integrated with FEA extractor electrodes. So the major advantage of this is, uh, instead it can emit instead half a millimeter at a much lower voltages. It's needed to reach an electric field sufficient, as we can see in this figure, the propellant with the help of a small conical nozzle and the electrode extraction. Here we can see the amount of charged particles being produced at a very low amount of voltage. So that much electricity is sufficient to extract ions, and or we can say colloids. So it enables a power thrust ratio scaling. Along with that, even the specific impulse and the thrust can be personalized itself. One major challenge is with the material, the type of material which can sustain this particular type of charged particles with the silicon structure itself, and it possibly overflows of the propellant out more than its particular capacity. Here is another image of a colloidal thruster. And here is a chart of some other propulsion systems, and we have tallied the performance, its advantages and disadvantages for all of them. So as here we can see, we discussed solid and we discussed colloidal. Here are some other types, that is vaporizing and liquid. So as per the performance need for the microsatellite, we can use this specific type of system which we need, depending on the amount of thrust and the amount of time for ignition. And each and every one, some have a simple structure, some have a very low volume, low weight. So, and even disadvantages are there, as there are both sides of a coin. And so we have pros and cons for each of the following system, which is detailed in this particular table. Moving on to the applications of MEMS systems, it is also used in many commercial areas such as inkjet printers, and also other displays, biosensors, and also other propulsion related applications such as accelerometers, inertial measurement units such as gyroscopes, magnetic field sensors, inertial navigation systems. Then we have fluid acceleration in nano satellites and many oscillators itself. Here is a schematic diagram of an MEMS. Here we can see a micro nozzle. There's an intermediate layer with titanium igniter, glass membrane, and the solid propellant is stored in this, and it is sealed with a layer. So, moving on to concluding with this particular topic, we can say that as of now, microthrusters can basically meet the needs of present microsatellites in thrust requirement, although some have to be tested on some spacecrafts. But we can say, according to the applications of current prospects and needs, they are still under the stage of research and developing whole as a technology. As of now, it is not mature enough, and we need more studies and more testings on these with more amount of investments. So it will be a mainstream trend after a few years due to its high performance, and the main factor is a small size and low power or electricity consumption. Along with that, it will also develop rapidly by strengthening on research, majorly focusing on the optimal design perspective. So, even the manufacturing technology for MEMS, along with its fuel section testing, and so on. So, if the measurement devices of thrust force can be improved to sustain its accuracy, it will be helpful for further developments of the microthruster. Thank you. Please do reach out to me if anyone has any questions. Thank you very much for your time.